Okay. Hello, everyone. We're going to go over EE330, everything about BJTs, just get more acquainted with the subject. And so for BJTs, the beginning part is we want to just understand how they work. So these are bipolar junction transistors. And what they do is they're known basically for being controlled by current, because if a small current comes into the base, that determines how much current is for the collector, for the output. So BJTs, they usually have an NPN here. So here we go. Here's our N and then PN. And so, or they can be like a PNP. They can look something like this. And so what we notice within here is the left-hand side is heavily doped. The middle is moderately doped, and the right-hand side is basically lightly doped. And so you need to know the concentrations of doping for each. And so what I like to think is this is usually 10 to the 19th. This is going to be, oh, let's refocus it. This is, the middle one will be 10 to the 16th, and the right-hand side will be 10 to the 15th. Same thing applies here, 10 to the 19th, 10 to the 16th, 10 to the 15th. And so now that we got that, what we need to see is that there are specific labels that you associate with each of them. And so the terminals here, this is the emitter, this is the collector, and here we have the base. Same thing here. We have the emitter, we have the collector, and then we have the base. And so we have the doping concentration specified specifically here, and we have those as well, and we have all the terminals. And so what we're going to notice is that this side is more heavily doped, this side's moderately doped, and this side's lightly doped. And so what we're going to see is when you are making transistors, the biggest key things you need to do is you need to minimize the components in the base. And so basically, the base will take small amounts of current, and it's going to amplify it. Current, oops, sorry. And the collector, so the collector will take a significant amount of the current. And so what we're going to see is IB compared to IC. And so what we're going to notice within our bipolar junction transistors is you can model it in a 3D model specifically and see what's happening within it. So I'm going to make it pretty large here just so we can understand the process. Because a lot happens within this. And so here we go. So this would be, most of the time we use NPN transistors. Compared to PNP, you can use one or the other. For this, we'll just show PNP because sometimes people like to see the movement of flows, but majority of the time they use NPNs because the mobility of electrons is about like 1350. They travel at a way faster rate compared to the mobility of holes, which is about 480. So electrons have a higher mobility rate than holes. And so then here, what we're going to see is that the main factor here, when we have our emitter, is that the emitter is going to emit those holes. The base is what is going to be input to there. So it's the N. So there's going to be a base current, which is electrons, and then the collector terminal, which is going to collect in usually the holes that are able to go from the emitter to the collector. And so we're going to see this. And so what's going to happen here is we're going to have a diffusion. And these holes are going to come over into this region. A few of them are going to fall into the base though, not many. And then, so what we're going to see is the diffusion of holes here. So holes, holes, holes. So it's going to be due to diffusion. And what you're going to notice is that this junction right here between the emitter and base is forward bias. The junction between the base and collector is reverse bias. Okay, so due to diffusion, a large amount of these holes are coming over to this side. And then only a few are coming right in the base region and actually recombining with electrons in the base. And then the majority of them, there's usually a type of, let's see, larger than this a little bit, but you would see it, there is a depletion region formed, and these dopant ions are left behind when the charge carriers move out of the region into the other one. And so we're going to notice that specifically the electric field goes from positive to negative. And so electric field goes from the positive to the negative end. And we're going to see when the holes fall into the electric field, since holes, we regard them more as positively charged, they're going to follow the direction of the electric field and make their way over here. So if they fall into the electric field, they're going to make their way over here and get into this side. So we're going to be able to put current in here and get it to the other side. And then these electrons here that are in the base, it's basically what's going to happen is some of them will be able to go back this way. Some will be here. And then some are going to come over from the actual P substrate or material here. These electrons will be either able to go right or left. And if these electrons fall within the electric field, remember electrons go in the direction of the electric field, they'll be coming in here. And so here we have IB3, which is the leakage current. Here we have IB2, which is the recombination current. And here we have IB1. And this is the electrons that are going over here. And what we're going to see is those electrons are going to make it to the other side here, but due to diffusion, since it's made easier. But for every 1,000 holes here, because it's 10 to the 19th compared to 10 to the 16th, for every 1,000 that make it over here, only one will make it over here. And so we're going to notice that issue. And then what we can say from this is because this is forward bias, the depletion region's pretty small here. It's not that large compared to the reverse bias junction. But what we're able to say from this diagram is that the base current we supply into it, the device is going to be equal to IB1, which is the ones that are coming over here. And that is the diffusion of these electrons that go back in here. It's the back end injection current. That's what we like to call it. So back end injection. And then here we have IB2, which is basically the recombination current here. IB2, which is recombination current. And then we have IB3, which is minus IB3. This is due to the leakage current. Now that we got that, we have all three. And now that we have all these currents, we're going to notice that the current in the collector will be proportional to beta DCIB. Big thing to take away from here is that we know that the collector current is determined by how much current is supplied at the base multiplied by the DC current gain. So our DC current gain, if we solve only for that, it's going to be the collector or output current over the input current, which is the base current. And so we like to call this DC current gain. This is our collector current. I sub C, and this is our base current. Okay, now that we got that, we're gonna notice that, as I said before, the forward bias junction will make diffusion easier. And what we have here is we have a greater concentration of holes basically in this region here, which is the emitter. And we're gonna notice that we have more holes here than in the base. Reason being is because majority of these holes, they make it to the other side, which is the collector. And so we're gonna see not many fall out because the base is usually made really short. So majority of the holes are able to get over to the other side. And we're going to notice that basically the current in the base is caused by three factors here. We have one, which is due to back-end injection, one that's due to recombination, and another one that is due to the actual leakage current. So one coming over. And what we're going to notice is that the biggest idea is you want to make recombination hard in the base. So you want your narrow base, but you don't want too narrow a base because that will make it will basically make IC go to infinity because your base current will almost be like 0. And so that's the issue. And so now that we got that, let's now go a little into the types of transistors. So let me get out, what are the main things? How do we know to distinguish between one and another? What are the main differences? How do we understand it? So let's talk a little bit about the charge carrier densities. And then we're going to get into biasing because that's where we focus the majority of the course on. And so charge carrier densities, what is happening here is we have three separate regions. Remember, forward bias is where it's made easier. Reverse bias is where it's made harder. So I'm just going to draw like the forward bias junction, the reverse bias junction. So here we have P is 10 to the 19th. And then we have N is 10 to the 1st. Then here we have P is 10 to the 16th. And then we have here is the amount of holes. Then we had here holes and then electrons. And so what we have here is P equals 10 to the 19th. N equals 10 to the 1st. Then we have the amount of electrons in the base is equal to 10 to the 16th. The amount of holes in the base is equal to 10 to the 4th. And then the amount of holes in the collector is equal to 10 to the 15th. And the amount of electrons in the base is equal to 10 to the 5th. And so here for our charge carrier densities, what we're going to notice is when we have what's going to happen. So remember, we're having holes come over, but not many. So we're going to get a lot of holes because remember, there's like 1,000 holes that are coming over here for every one electron, but not many will be coming back. So the majority of the holes will be brought to the other side here. So we're going to notice that there's going to be an increase in holes on the actual collector. If there's an increase in holes in the actual collector, then the amount of electrons is going to be pretty small, like 10 to the -2 now because of that, because there's a large number of holes coming in here. There's going to be more and more holes, and so less electrons, but it will return to equilibrium after a few diffusion lengths. And then what we're going to see, when I mean due to diffusion lengths, it's because they're recombining the holes and electrons to return to their equilibrium values. And then here, we're going to see that due to the holes leaving and just a little electrons coming in, I'm going to reference that something like this. So there's some electrons that are coming back over. And so, but that will return back to its equilibrium value in a faster amount of time because there's less electrons compared to the amount of holes that are going over here. And then here we have about 10 to the -3. And so what's going to happen is because there's just a few because we have some electrons coming in here, remember, due to the leakage current, this will return back though to zero, its equilibrium value. And now that we talked about the charge carrier densities within our transistor, that's due to, because these holes, not many are gonna recombine in the base, so we're gonna get a lot of holes now in here, so therefore the electrons will be impacted. Over here, there's gonna be a few electrons coming due to leakage current, so there's gonna be more electrons, but as you go out further, there's gonna be less. And then there's gonna be some electrons here, but they're gonna die off because some will come through due to back-end injection. And so now that we got that, let's talk about biasing. And so biasing, what we have in it is simple biasing, we have stabilized biasing, and then we have current source. So we have simple biasing, which is a mode where it basically varies directly with beta DC. Next one is we have stabilized biasing, where it works but has limits. And then finally, we have a current source. We don't really get into this though. So what we're going to see is the biasing. Why do we use it? It basically establishes the Q point, which is your operating point. And so right there, the Q point, your operating point is basically defined as what's the amount of collector current, what's the amount of collector to emitter voltage. That's what your operating point is. Because when you look specifically at a transistor curve, you're going to notice that you have these characteristic curves here. Something like that. And it's usually given by BCE here in IC. And you're gonna notice that like they draw something, it looks like this, and then they have another one. There might be like other curves in here, but it looks something like that. And then you have IB set here is equal to some set value. When IB is here, it's gonna be equal to that. And you're gonna notice that the max voltage you can get is VCC. And the max current you're gonna get is gonna be equal to VCC all over RC. So that represents the max point for both. And so people usually like using that because you're able to determine the Q point, which is sort of like the middle point in the curve graphs. And so this is the point where basically it's gonna stay in active mode. It probably won't fall into saturation mode. And so what we like about this is it's a nice point because it is like in the middle between, but there are some limitations where maybe it's using more than that's required. If it doesn't go into saturation easily, you might be able to lower the amount of voltage, but that is what they mean by Q point. It's usually like the operating point so that it remains in active mode. And so it's really good to see a diagram. So let me pull it up on the left-hand side for you guys. It's going to be the 3904 transistor characteristic curves. And so if I look at any images here, what we're going to see from the characteristic curves here is that they follow the same suit, but let's look at modes because they identify them, which I find really helpful sometimes to just know where, okay, here it is. Here's a really good diagram that I'm gonna label also on the right-hand side. And what you're going to see is that they call the maximum to the maximum, that's the load line. It's sort of given the name that. So this is the load line. Here we got certain regions. So within here, we have the active region. So this is the active region. And then within here, we have the saturation region. So So that's the point right here. And then within here, we have the cutoff region. And so what I want you guys just to understand here is that the active region is where it's going to stay, like, you know, in the good range of values, where it's going to be able to amplify. It won't be cut off. And so, you know, like when cutoff occurs, and then like the voltage would be like distorted, something like it's going up like a cosine wave, then it's flat, then it's going down, flat, then going up. It's not like your normal waveform here. And that's what you want. You want this type of active. You don't want it to fall into saturation where it cuts it off. And so, or the cutoff region. Those are what you want to avoid. And so there's 4 modes for the BJT. And these are pretty significant to know each type of mode. Number 1, you have active mode. Number 2, you have saturated mode. Number 3, you have cutoff mode. And finally, you have inverted mode. Active mode, that emitter to base junction, it's forward bias. So I'm going to represent that. I'm going to say here for each of the modes, the emitter to base and then the base to collector junctions. And so what we're going to see is this one's forward bias, this one's reverse bias, and then the saturated mode, what we're going to see here is that's where it's going to be saturated is sort of like on mode. So it's stuck in the on position. It's like your switch. And so it would be both as forward bias. If both are forward bias, then it would be made extremely easy for then all the holes to go over to this side. And because it'd be extremely easy, what's the point of having a transistor if the same amount going in is the same amount going out? That's just like a switch, right? A short. And so that's why we don't use it. Cutoff mode is like an off mode. And so that basically says that if you're able to put it in cutoff mode, what you're going to see is that one of them is, they're both reverse bias. Reason being is because it's going to make it really hard for any to, because reverse bias, these holes aren't going to be able to flow over the junction easily. And so that's going to make it hard for holes to get to the other side. And therefore, it's going to be even harder for them if they can barely make it over here. They're stuck over here, and then they have to overcome another reverse bias junction. So that's pretty hard. So that's why when both are reverse bias, it's in cutoff mode, which is the off mode. And then inverted mode, which is the reverse of active mode. And so here you have the exact opposite, where the emitter base junction is reverse bias, the base to collector is forward bias. And so that's all the specific regions I have within the transistor, the 4 types of modes you can have on this BJT. And now that we saw that, let's try understanding. I feel that a lot of times we get confused under which type of configuration it is, and we don't know which formulas to use half the time. And so let's just try making a tree map first, and then we can go back to the problems and try solving them. But I feel like without a good tree map, we don't know where to start. And so let me pull that over here. Okay, so within our tree map, we're going to have BJTs. So this is where the bipolar junction transistors occur. Junction transistors. And basically within our BJTs, it can either be unstabilized or stabilized. And so that's where I would first break it down to. And so there is unstabilized designs. And then we're going to have stabilized models. So this is the big point where I think a lot of the times we don't know what makes it unstabilized and what makes it stabilized. Well, stabilized 1 is where the collector current changes with temperature. That's why we don't like to use it a lot, because it changes so much with temperature. For the stabilized design, IC doesn't change with temperature. And so that's what we're going to have there as well. And so what we're going to see with the unstabilized is that it will look like this. So we're going to have our VCC here. And within our model, we have an RC. And we have and this one makes sense. And we have an RB. And so then we have an RB here. We have an RC there. And so what we're going to notice basically from here is that you're going to be able to tell that the voltage across resistor B, that's going to be equal to VCC minus V, and then here's the base to emitter junction. This is what we like to call VBE, because it's from the base with respect to the emitter, and the emitter is at ground. So that's why we call it VBE. And then, so what we can write for an equation here is voltage on the base resistor is going to be equal to VCC minus VCE, or sorry, VBE. And then here we're going to have IB is equal to VRB over RB, which equals VCC minus VCE all over RB. And then we're going to see that IC is equal to beta DC IB. And what we're going to see from this is that this makes sense, right? Because it's the current gain, and we know it fluctuates with how much current you put into the base. That's going to determine how much you have on the collector. And then we also know the current in the base is going to be how much voltage is actually across the resistor divided by the resistance. So that's VCC minus VBE, sorry, I accidentally put VCE. So minus VBE all over the resistor of the base. Now that we got that, let's look at what are our DC parameters here. And so the DC parameters, notice that all these equations I just derived from the model. They're very simplistic. So VCE here, the voltage between the collector to emitter is going to be equal to VCC minus ICRC. And that is going to also have IC is equal to VRC all over RC, which is equal to VCC minus VCE all over RC. And so that's what we're going to notice. And then we're going to see that IC max is equal to VCC all over RC. And so what I like to do a lot when I'm given these DC parameter models, I know this feels like it's a lot of equations right now, but your DC parameters, the main two things you focus on is IC and VCE. And then what you want to check, is it in saturation or active mode? You do the test. Is IC max less than IC? And then if so, then what's going to happen is, because your current is greater than the maximum current, you're in saturation mode. And then if you're in saturation mode, you have to use the ICEO is equal to beta DC ICBO, which is like 2 nanoamps. That's what this is. And then if not, you're in active mode. In the active mode design is basically that would mean that your IC max still hasn't been reached. So you still have that perfect wave shape and it's not cut off like in saturation mode. And so that's what usually I determine when I first see a design that's like this. I'm like, okay, this is unstabilized. I don't see any emitter resistor. I don't see another resistor here, R1 and R2. So I'm like, okay, this is unstabilized design and it's going to vary with temperature. So IC is not going to be pretty constant at all. And the big equations that come into mind are my IC is equal to beta DC, my DC current gain times the current at the base. We're going to have that the DC parameters here are the voltage between the collector emitters equal VCC minus how much current is flowing through, this RC here, and then times RC, which gives you the voltage drop there. Then IC is equal to VRC over RC, which is VCC minus VCE all over RC. IC max is given by VCC over RC. And then we're going to see that for IC max less than IC, if that exists, you're in saturation mode because you have overcome the max current. If not, then you're in active mode. So this test is really good to know too. So these 3 items you should know basically when you are consulting this circuit. The other type of design is stabilized. And so stabilized design, this one is a bit different. And so the way I want to say that it's different is because we started out learning stabilized designs looking like this. And so let me just separate this side from the other. Oh, fine. Okay. So for stabilized, we started with the DC model. And so for a DC model, what you're going to realize is that here, here we have R1, R2, and we have RC, RE, and then we have VCC. And what we used to say about this, some equations that we came up with was at this point specifically, which is VThev. VThev is equal to VCC times R2 all over R1 plus R2. Because that's the point right here. How much voltage is actually on this at this point? It's how much voltage is on this resistor. And then that voltage on that resistor is just a voltage division of how much is actually supplied to the source. Your R Thevenin, so how much resistance is actually at that point? That's going to equal R1 in parallel with R2. And so that's your R Thevenin. Now that we went over the DC model, a few of the equations used with your DC model, because your IC doesn't change much with temperature, you're going to notice that I'm going to define those DC equations, which we're going to say is for DC parameters, it's going to be IC is approximately IE. Because remember, the amount of current supplied to it is the amount that goes for the collector because that's the majority of carriers. So this is going to equal V Thevenin minus VBE, because to determine the emitter current, that's usually given by how much current's going through here. So the emitter current's approximately V Thev minus VBE. So of course, this voltage minus the voltage here, and then that'll give you the voltage here, and then divided by the resistance. And so that's what we get for our one DC parameter. Our other one is VCE, which is equal to VCC minus IC, and then RC plus RE. And so those are the two equations you should be familiar with, because VCE is the voltage drop from the collector here to the emitter. And so VCC minus IC, the current traveling through this resistor, plus the current traveling through this resistor. So VCC minus voltage drop here and voltage drop here will give you the voltage drop from the collector to emitter. Now we have the three types of stabilized designs. So this, just so you know, was when we're looking at the DC model. We only defined DC parameters because DC was the input. And so that's why we have these equations here. And now we have certain types of configurations to go along with this. So we have a common emitter configuration, common emitter. And so within our common emitter, you have the common emitter without degenerate, amplifier without degeneration. Degeneration. So degeneration means you're decreasing the gain. And what do I mean by you're decreasing the gain? Well, that basically means that whenever I'm decreasing the gain, that means that my resistors are going to more heavily control the circuit, because there's going to be a larger voltage drop we're going to see across that RE. However, when you don't have degeneration, that means more of the voltage drop is going to occur on the collector resistor in comparison to the emitter resistor. So here we're going to see more voltage drop across RC. So let me draw out the circuit. This is my RE, this is my RC, this is my VCC. Here's my R1, here's my R2. And then here is our transistor. And what's going to happen is it doesn't have degeneration. So what this does is this provides an AC ground here. And so that's why we call it common emitter, because it's common to both the input and output. And so if you have an input here, you have a voltage source usually connected to some ground. And then our output, we usually measure it right across here. So this is usually V out here. And so our output voltage, what we're going to see when we're looking at the AC mode, it's going to be with reference to ground, because if we're only dealing with AC mode, this would be with reference to ground. And then the input voltage source here would be, let me draw just like what the input voltage source would look like, so you guys actually understand what I'm saying. Here we would have a, pencil. Let me just draw this for now. We'd have something that looks like a voltage source here, an RG, and then this would be our voltage input. And so what we're going to notice is that in AC mode, which is probably going to be the supply here, in AC is supplying here. And so what would happen here is this would be connected to ground. But in AC mode, we're going to notice the voltage output, this would be like a ground, because this is DC right now, but it'd be like a ground here. And also, I forgot, in AC mode, you need a capacitor here, because a capacitor blocks any DC signal from coming through, and it permits AC signal to get through. And so we want to get a lot of this AC signal at the base in order for it to be amplified. And so that's why we use a capacitor here. It's because it allows the signal to pass through and get to the actual base. And we want that signal being amplified. And that's the reason we use the transistors for amplification. And so now that we know why the common emitter has a name it does, because the emitter resistor shares basically an input in the output also. It shares a common terminal with them. Now we need to actually know what are the DC parameters here and what are the AC parameters for the circuit setup. And so for DC parameters, what we have is we have VCE is equal to VCC minus IC RC plus RE. And then we have IC is approximately IE, which is equal to the voltage across the emitter resistor all over the emitter resistance, is equal to VThev, remember, minus VBE all over RE. Same equations you have for your DC parameters, which is nice. It's the same ones you repeat over and over again. And you're going to notice that later on as well. The only thing that is changing up is the AC parameter. So I'm going to stop writing the DC parameter values because they're the same for all these, which is nice when it works in DC. But most of the time, we are working with an AC signal at the input. So therefore, we focus a lot on how much gain are we getting of that signal, how much of that signal is actually going through. And so for my AC parameters here, I'll do this in another one, but we have our AC parameters, which we're going to see AV isn't equal to negative. And then here it would be VRC, the voltage on collector resistor, all over the Thevenin voltage. And so what we're going to notice is that the input resistance here, so Rn, is going to be equal to R pi in parallel of R1 in parallel of R2. Big thing to remember, we're working in AC right now. R pi, remember, what is that defined as? It's B naught VT all over IC. There you go. So we have our AC parameters here. And then the last one is R out. So R out is equal to RC in parallel with little RO. And what you need to remember is little RO is equal to VA all over IC. And so those are all the parameters you have for AC mode. There you go. And that's for your first one, common emitter without degeneration. The reason why it provides basically a large voltage gain, but it's not as stable in the amount it's going to give you for that voltage gain. It can fluctuate a lot with temperature. So that's why I'm going to list advantages and disadvantages here in this part. Advantages / disadvantages. The nice thing about this circuit is it provides high gain, but it's not accurate in the gain. It fluctuates with temperature. And so you're going to notice that here, VT is going to be 0.019 and then 0.026 and 0.035. And that's going to be the values. So let me write that off as a side note here. Maybe it would be good. I'll put this actually in the upper right corner. Okay, so for VT, it's going to be equal to, here what we have is 0.019, and then 0.026 and 0.035. This is going to be for temperature is equal to -55°C. Temp is going to be equal to 125°C. And temp is going to be equal to, oh, sorry, that's room temperature, sorry, 25°C. And then temp is going to be equal 125°C. Okay, sorry. Going back to the models now. So we can see it's not accurate in the gain because the voltage here is going to fluctuate a lot with temperature VT. It can change from 0.019 all the way to 0.035, which is about almost, we're going to see double of what it could be. And then now that we have covered this for the common emitter without degeneration, let's get into the next type of circuit. And so this one, we're going to see the common emitter with partial degeneration. So we're going to look at that one and analyze the circuit. And so here, we're going to have common emitter amplifier with partial degeneration. And so here, what's going to happen is basically we're going to have this one where it's R1, R2, and then we're going to see that RC we still have the transistor. Then there's going to be RE1 and RE2. And then we're going to have the emitter capacitor, VCC here, RC, then we have R1, R2, and we have RE1, RE2, and then capacitor, the emitter capacitor. And then here we have basically what you're going to notice within this design is that it's going to have, for partial degeneration, a compromise between these two. And the way it does the compromise, what you're going to see is that, let me first draw this and draw this to the base coming in here, is within its AC parameters, you're going to notice how that effect actually takes place. So I'm just now going to write the AC parameters since the DC parameters are the same for all. So AC parameters, that is going to be AV is equal to negative RC all over 1 over GM plus RE1. And then what's going to happen here is then we're going to notice that Rn is equal to Ri plus RE1, 1 plus beta naught, R1, R2. And then we're going to notice that R out is going to equal RC in parallel with little RO. And that will be, so we notice that R out might be the same. R input, though, it's going to be a little more. And the reason why is we're going to notice that this RE1 here is going to be 1 plus B naught greater. And the reason here is we had a bypass capacitor, so we didn't even take RE into account. We're here, we don't have a bypass capacitor for RE1, so that's why we have to actually take it into account here. And then we have it in parallel R1 and R2. And so that's why we have these equations for AC parameters. And then what's going to happen is here, we're going to have the common emitter with full degeneration as our number 3. Oops, sorry. Oh, sorry, I forgot to list advantages and disadvantages of this. So let me do that in green real quick. So the advantages and disadvantages of this, disadvantages. The number 1 is that it provides more of, it's like a balance between the two, I want to say, of the full and the without degeneration. And so what I would say here is that the nice thing about it is it provides accuracy in the gain. but it's like not as high of gain, but it's better than the full. So I'm gonna just put it, it's like moderate gain. It's not really great, but it's not bad. It's like around like 20 or something. It's not like huge, but it's not small. Like 20 is still a good number. So the last one is common emitter with full degeneration. Here we go. And this one here is going to be common emitter with full degeneration. What we have here within our circuit is for the full degeneration, it's going to look like this. So it's going to have no capacitor. So therefore, there is a small gain. And you're going to see, because more of the voltage drop will now occur, we're going to have more voltage on RE. RC, or here, then we have R2, then we have RC, then we have VCC, and then we have RE1, sorry, just RE, is down, and then it's RE here, 20 RE, and then we have this to ground. So what we have here is for our AC parameters, we have basically AV, what is it going to be equal to? Well, it's going to be a smaller gain, of course. And so what it's going to be is negative RC over RE. And then what's nice is this gain, it has nothing to do with beta. Or temperature. High gain accuracy, but small gain. So this is sort of like, I guess, the advantages and disadvantages of this design. So let me circle that. And then what we're going to notice, what's the next parameter? Well, our input. Now it's going to be, because we have now RE, there is no bypass capacitor. We actually took that into account in the input resistance equation. So it would be R pi plus, and then here we're going to have 1 plus beta naught, and then that'd be times RE. Okay, let me just rewrite that because I ran out of room. So it's going to be equal to R pi plus 1 plus beta naught RE. And that whole thing is going to be in parallel with R1 in parallel with R2. And so that's going to be what we have for our input resistance, and our output resistance would be RC in parallel with little RO. And so that's what we have here. And so what we have is our 3 types of designs, and then we need to get our common base and our common collector. And so a common, why do we use common bases and why do we use common collectors? So now, after we got all of our AC parameters, let me just circle that real quick. Then we'll get into the common base. So when I have a common base, what does it give me? So basically for a common base, we don't use it because it has a low input impedance. And we usually use with a common emitter and at high frequencies. So that's what we have here. And so what we're going to notice is that the common base is going to have a configuration here where it has R1, R2, and then we're going to have a collect capacitor here. And then we're going to have a resistor here. We're going to have, this would be RC, and then we're going to have a voltage source connected. VCC. And then our other terminal here is going to be RE. And then we're going to have our voltage input. Just like, oh, sorry, I forgot, but the voltage output for all the common emitters, I labeled it on this first one, but in case you want to know, just in case, the voltage output's always there. And then right below the collector resistor. So the common base, what's going to be on this one is it's going to be the voltage input is going to be over here. Like with the common emitters I drew, sorry, the voltage input is on this left-hand side here. The common base, the voltage is actually on the emitter side. And then we have our S. People like to call this RG, RS, same thing. Voltage in source resistance, other people use it as RG, they just call it by name. I like RG more, personal preference, but the common base, the main thing about that for the AC parameters is you're going to notice that AV is going to be equal to the voltage specifically on that collector resistor all over VT. And then you're going to have R in, it's going to be equal to 1 over GM. And then this is going to be in parallel with RE in parallel with little R pi. And then your R out is going to equal RC in parallel with little RO. Nice thing about all these equations, I guess except the common collector, is that all the R outs are the same. But then at least in, you know, common bases, they're really not used. I think he'll only like question us like, oh, when would you see one? Or like it'd be at high frequencies, but because they have low input impedance, they're not highly used within the device, so you know. And then the voltage output would be right here. So this is where V out would be, and then here's where it's whatever. Okay. The next one we're going to have is going to be the common and common base. We have common collector. And so the common collector will be the final configuration of the transistors. And so I'm going to put that, get my other paper. Okay, so common collectors. So if we have a common collector, okay, why is this common base? Well, it's common base because if I loop in AC mode, it's going to ignore this and this would become a ground. So the output tied to ground, and then the input has ground here. And so the base is tied to ground as well. So we're going to notice that the base shares an input to specifically the output and the input to the source. So because the base shares a common terminal between the input and output, it is going to be the common base. The common collector, we're going to see the final configuration, what that should look like. So for the common collector, what you're going to have is it's going to have a voltage supplied. And this is where it's actually tied directly. You don't have a collector resistor. So that's the one nice thing, the common collector. And then you have R1. R2. And then you're going to have, this would be like your source again. If you want to draw it. Oh, I guess I forgot the capacitor and the other one up here. Let me just draw that real quick. Here, it would be, what's nice is it sort of follows suit to a common emitter, your voltage input, and then you have a source resistance. And then you would have, what we would see over here is what we'd have is our emitter resistor. We'd have output voltage here. And now that we got that, is we got specifically our output voltage, our RE, our VCC, and then we have R1, R2, and RG and VN. And now that we got that, we need to get specifically, why would we use a common collector? Well, we would use a common collector because people like to say it has low resistance at the output. So you can produce more voltage on your load resistor. So that's a nice thing, is it has low output impedance. So that means it can drive more voltage to the load. And then this just basically says R out is small. And generally, RL is small. And usually like your load resistance is 100 ohm or 50 ohms. So we're going to see why you would use this. But the AC parameters here, you're going to notice that the AC parameters, what are those going to deal with? Well, the AC parameters, what we're going to see is that AV will equal RE all over RE plus 1 over GM. The reason this amplifier is it doesn't have much gain, because 1 over GM is about 0, so it's RE over RE. And so the gain's not, it's a gain of 1. But it provides high input impedance and low output impedance, which is really nice because then you can amplify only the signal you want to, and you can drive a load that is pretty small resistance. So this is about 1. And then your Rin is equal to R pi plus RE beta naught plus 1 in parallel of R1 parallel of R2. And then your R out is equal to 1 over GM plus R, and then you can say RS or RG. I like RG personally more. It doesn't matter. That's your source resistance in parallel of R1 parallel of R2. And all over beta naught. And then here, your AC parameters. So now that we went over those different types of transistors, I know it's a lot to keep in mind which transistor when. And so the number one thing I'd suggest is just go back to the beginning. And let's recap it real quick. So a bipolar junction transistor, it basically has current that is going through it, and it's going to determine how much of that current actually gets to the output based off how much current is coming in. So how much is that gain factor going to be? Your beta DC, which is your DC current gain, the amount of collector current over the amount of base current. So you have two types of designs. You can have unstabilized or stabilized. In your unstabilized, IC changes with temperature. But in your stabilized, IC doesn't change much with temperature. Reason you know it's unstabilized is because you don't have another resistor down here or an emitter resistor. Compared to here, you have an emitter resistor and another resistor. And then you're going to also notice specifically in your DC parameters, VCE, which is the voltage from the collector to the emitter, is going to be equal to VCC minus the voltage drop across the collector resistor. That's what we have here. IC would be the voltage drop across here divided by the resistance here. And the big thing to check when you're doing these problems is IC max less than IC. So is IC greater than IC max? If so, you're in saturation mode. And so be ICEO is equal to, that means an open between the collector emitter, base is open, so it'll only be involving this, no base input. And you talk about ICEO. And then it'd be equal to the DC current gain times the collector to base. What we have is 2 nanoamps. So this would be the emitter open, so it'd be 2 nanoamps times and whatever gain this is. A special note here is the 3904 has about a DC current gain. Beta DC is about 200. And so that's just a nice value to know with your resistors, the 2N3904 transistor. That's the only one I have memorized for the actual current gain. And right here, we have stabilized models. These are where IC doesn't change with temperature. So we're going to get a DC model here, which is V Thevenin equals VCC multiplied by R2 all over R1 plus R2. The reason this, do not confuse it. Please don't. I did this as well. Don't confuse it with this one right here, the common emitter of full degeneration. The reason why is because we're looking at this with an AC input here, but this one is only in DC mode. So like this is only DC. We're not having any AC input here. And so right here, IC, the collector current's about equal to the emitter current. That's going to be VTheb minus VBE. So VTheb minus VBE, you get right here, which is VRE all over RE. That gives you IE. VCE is equal to VCC minus IC times RC plus, and then the voltage drop here. So you minus that from VCC and you get VCE. DC parameters, you're going to see without degeneration, that means that you're going to have a higher gain because this impedance is going to be about 0. So the voltage across this collector resistor will be a lot greater than the voltage here. And because the voltage on the output is a lot greater than the voltage on the input, we're going to see a high gain. So what's going to happen here is it's the same DC parameters as all of them, but the AC parameters, it's the voltage across the collector resistor all over VT. Here it's going to be R pi in parallel of R1 in parallel of R2. And the reason we don't have our emitter in here is because it's in parallel with the capacitor, and the effective impedance is about 0. Because remember that 1 over 2 pi f, that gives you the frequency, what you're going to see, because it's 1 over omega c, so 1 over 2 pi f times c. And you're going to notice that this capacitor, if you combine it with the resistor, the effective impedance will be 0. And the nice thing about this is it provides high gain, but it's not accurate in the amount of gain it will give you since it can fluctuate with temperature. The next one is the common emitter partial degeneration, which the gain equation we gave right here. It's negative RC all over 1 over GM plus RE1, because there will be some voltage drop across here because now we don't have a bypass capacitor. So that's why it's now in the gain equation. And then this resistor will also have some resistance to it because it's not bypassed. So the effective impedance is not 0 anymore. So that's why we include it in the resistor input equation. The output resistance, though, is the same. We haven't modified anything there. The common emitter full degeneration. Nice thing about this one is you have basically high accuracy in the amount of gain, but it's very small because now your input resistor is even greater now. So you include R pi plus 1 plus beta naught, RE in parallel of R1 and R2. And then R out is the same as all the others. So it has nothing to do with beta or temperature, but has a high gain accuracy but small gain. Common base basically has a low input impedance, usually used with a common emitter and at high frequencies. So it's VRC over VT, and it's 1 over GM in parallel with RE in parallel with R pi. Reason, here we don't have R1 and R2. Well, our input is actually now looking at this side, which is RE. So we're on this side of the equation. And then in parallel with R pi, that's what we're used to seeing. And then 1 over GM. R out is RC in parallel with RO. More. And then the last one here is the common collector, which we use because it has low output impedance, so it can put more voltage on the load. And RO is small, and generally RL is small. And so what you're going to see is the load resistance is small and the output resistance is small. So there can be more voltage across RL. So that's why we usually use this as the last one. Well, you don't like it because the gain is about 1. Because it's just RE all over RE plus 1 over GM. So gain's about 1, which isn't good. But then we see that the input impedance, it's R pi plus RE, beta naught plus 1 in parallel with R1, R2. And then our output impedance here, it's going to be 1 over GM plus. And then what we're going to notice is that RG is now in parallel with R1 and R2 if we just look at specifically what these would be connected to. If you see, all those would be in parallel because they all have the same common terminal. So that's why they're all in parallel, all over beta naught. And then that's how we got all of our models. Now that we got that, let's try and do maybe a few problems. So we're going to work through some examples here. And so the first one is going to be our first example I'm going to put here is the temperature is going to equal 25 degrees Celsius. So that's room temperature right there. So your beta DC will equal 200. And let's start with the first transistor problem. And so we're given like something like this. We have a 50K and we got a 20K. 20K. And we have a 13K. Then we have a 5K. And then we have it connected to ground. And so what we have here is we need to find values for IC and VCE. Well, those are nice. Those are DC operating points, IC and VCE. And so let's try to determine what type of design this is. And so this looks pretty much like my DC model for a stabilized design. So right here, I'm stabilized because I have a resistor here and here. So I'm like, okay, it's under stabilized. And this looks like a DC model because I don't have any AC mentioning, no voltage input here. And so I'm going to say that this is a DC stabilized design. Okay. And so let's now check, is it in saturation mode? Is it in active? We don't know. And so we need to do IC, which is approximately IE, which is equal to VTEV minus VVE all over the emitter resistor. VTEV here is going to be equal to VCC R2 all over R1 plus R2. Equals, and then our voltage to source is 12 volts. Times R2, which is 50K, all over 20K, plus 50K. And then here, got that equal to, and then now let me get my calculator out and perform that calculation for you guys. It's going to be, okay. So we got 50 divided by 70 times 12, 8.57 volts. That's how much I got for my VTEV. And so now that we know VTEV, we can do 8.57 volts minus voltage base emitter is 0.65. Maybe 20K over 20K plus 50K. Yeah, you're right. Thanks. Thank you for catching that. Smart move, John. Thank you. 20 e to the 3 divided by 20 e to the 3 plus 50 e to the 3 times 12. So I got 3.42. 3.42 volts. Here, just 3.42. All of minus 0.65, all over emitter resistor, which is going to be 5K. So 3.42 minus 0.65 divided by 5,000. 555 microamps. And now that we got IC, our VCE, what is it? VCE, that's the voltage between the collector and emitter. That's going to be equal to VCC minus, and then the current going for this resistor, which is IC times RC, plus the current that's going for this resistor. Get both voltage drops, minus them from each other. So 12 minus IC is 555 microamps times 13K plus 5K times 18 e to the 3. 12 minus, so I got 1.997 volts. There you go. That's the voltage between my collector and emitter. And so that's how I was able to solve for IC here in VCE. But what was one important check I might have missed there? Is I didn't know if it's operating in saturated mode or active mode. So this might not actually be correct. And so let's check, is it in active mode or saturation mode? Well, how do we check that? We do IC max. Let's see and compare it to IC. If it is greater than IC, then we're in active mode, and then we're fine. IC max is going to be equal to VCC all over RC, which is going to be 12 all over, and then the collector resistor is 13K. 12 divided by 13 e to the 3, which is 923 microamps. And so is IC max greater than IC, 923 microamps? Is that greater than 555 microamps? Yes, yes, it is. So therefore, we are in active mode. So we were good. But you should always do this check at the beginning. Once you find the value of IC, you should always try and see, is that now an active or saturation mode? That's a big part of your design that you need to make sure. And now that we designed that, let's go on to the next one. So in the form of Caesar and transistor. Okay, I'm just going to go into transistor problems. Okay. So let's do number A here, and then maybe we'll try doing D2. And so this is from handout 2, or sorry, handout, which one? Handout 4, and let's do my approach to 1A and D. So it says find IC and VCE at 25 degrees Celsius for beta DC typical. Okay, so number A is where we have 12 mega ohms. And then we have -4 volts for the okay. We have 10K. Then we have oh, one other check that might be really good. I guess I should start a checklist always when you're starting circuits. So let me actually add this over here. Because when you start it, whenever you approach a problem, number one, you should check if in active mode. So this would be like your IC compared to IC max. It's an active mode if IC max is greater than IC. And number two, you should be check if NPN or NP or PNP makes sense. And so for an NPN, there's a positive voltage, so plus VCC supply, but the PNP, there's a negative voltage supply. I always think of the middle term is what determines. And so those are your two big things. So here, what do we have? Well, this is a P because this must be an N where the diode's pointing into, then a P. Negative supply, yes, that's correct. And so now we need to do, here we have, this is unstabilized. And the first thing I can tell is because there's no other resistor here and there's no emitter resistor in this one. And so this is an unstabilized design. And so what we're gonna have here is we're gonna have our IC is gonna equal, and then beta DC times IB. You can say that, and you can do like, what's the voltage on the resistor base? You can also try using the equation I gave you, which you can do IC is equal to VCC minus VCE all over RC. This one's a little different for the IC, you have to approach it, but it says for beta DC typical. And how do we find beta DC typical for a transistor? That's a 2N3798. 2N3798 transistor data sheet. And when I'm looking at this transistor, we want to find the DC current gain and, oh, let me get a PDF actually. 2N379, yeah, this should work. And here we got a beta, does it give us a beta DC at all? Okay, here's a beta DC we're working with the 3798. Usually there's a curve, but it looks like here they didn't give us a curve. So I would guesstimate, they gave us a min and max here for one at least. But I would say around 300, pick a middle value. But I'm pretty sure RE will supply these on the exam or only do the 3904. But I would just pick a middle value because none of the other maximums are given here. And so I would just go with 300 for my beta DC. But now I still have to determine IB. Well, IB is going to be the voltage on the resistor base, right? All over resistance base, just Ohm's law there, which is going to be equal to VCC minus, and then what we're going to get is voltage between the base and emitter all over R. Is this voltage over here? Oh, sorry. Switch over here. This voltage right here minus the voltage at this point here is going to give me the voltage only across this resistor divided by that resistance. It's going to equal -4 plus 0.65 all over resistance. The base is 12 megohms, which we have -4 plus 0.65 all divided by 12 e to the 6 is equal to, and then here, what I get specifically, you get a 279 nanoamps, which is pretty small. But remember, that's multiplied by 300 here to give us IC, 279 nanoamps. And what I got specifically was, so times by 300, -83.75 microamps. And then what I know from this now is I know, oh, sorry, you can't see that. But I know my IC, but what's my IC max? I want to see, is it an active or saturation mode? That's equal to VCC all over RC, which is -4 volts all over the collector resistor, which is 10K, which would be -4 divided by 10. -400 milliamps is what I got. And so now that I know that, I can say that IC max is greater than IC. So you're in active mode. So we're good, we're in active mode. And so now since we're, sorry, I keep cutting you guys off. Since we're in active mode here, and this is the set value for IC then, well, now we need to determine VCE. VCE, I'm gonna just write it here so I don't go onto another page, is gonna be equal to, and this would be VCC minus ICRC. Because the only voltage drop that can occur here is across this resistor, which is -4 minus, and then IC is -83.75 microamps times RC, which is 10K. VC -4 plus 83.75 -6 times 10K is -3.1625 volts. Voltage between collector and emitter is equal to that. And so now we determine the values for IC and VCE. So now we got that. And also heads up, everyone, I'm pretty sure our professor's solution problem is wrong because the solution says, but that doesn't make sense. Oh, okay. Yeah, because if we verify what we did versus what, this makes sense in terms of active mode and saturation mode, which one is it in? And that's funny because he doesn't deal with cutoff mode mostly. So we're good here, I would say, because we used all the mathematics to prove our design. And so number 5, let's go to it. So here, oh, sorry, I was going to do part D from that one. Almost forgot. So this one's now stabilized design over here for part B. Here we have 6K, and here we have 3K. And then we have a 500. Then we have it coming down here. Then we have it 200. And then we have a ground. And then we have a 12-volt source. And now we got a 2N3946, which now that we got that, what are we going to do specifically? Well, remember, first thing, determine what type of design this is. I'm looking at it. It has a resistor in here and emitter resistor. So this is stabilized. Oh, let me put that here. And since we have a stabilized design, is this only dealing with DC? I don't see AC in here, so I'm just going to say this is a DC stabilized design. So stabilized DC model. And now we have that. And what's happening here is we need to determine our IC, which is going to be equal to, and then remember, IC is roughly IE, which is equal to VThev minus VBE all over, and then RE. Remember one of my first checklist items, it was, this is an NPN, makes sense. We have a positive voltage at the source. I look at the middle term, that's how I remember it. And so IC is approximately IE, which is equal VThev minus VBE over RE. VThev is equal to, and then this is going to be VCC R2 all over R1 plus R2. Just going to be equal to 12 volts times 3K all over 6K plus 3K. And so we got here, it's going to be 1/3, oh, sorry, yeah, 1/3. And so 1/3 of 12 is going to be 4. VThev is going to be equal to 4. Now we got 4 minus 0.65 all over the emitter resistor, which is 200. Now we got that, which is 4 minus 0.65 divided by 200. I got 16.75 milliamps. 75 milliamps. And now that we got that, we got VCE. VCE is going to be equal to VCC minus IC, and then it's going to be RC plus RE. And so now we're going to do 12 minus we're going to have 16.75 milliamps multiplied by RC, which is going to be 500 plus RE, which is 200, BCE, which is going to be 12 minus, we're going to have 16.16, and then times 500 plus 200. So we get 275 millivolts for VCE. Now that we got that, what do we have here? Well, we have 275 millivolts. This is great and all, but I forgot to check. Is this an active mode or saturation mode? Well, you remember the check. Is IC max greater than IC? If so, you're in active mode. If not, you're in saturation mode. So let's do IC max calculation. It's equal to VCC all over RC, which is equal to 12 all over 500. 12 divided by 500 gives me 24 milliamps. Okay, you can see IC max is greater than IC, which is only 16.75. So we're in active mode. So we're good. So our answer here is 16.75 milliamps, and our VCE is 275 millivolts. So you're good. Now that we got that, let's go to BJT, homework number 5. Let's see if we have any questions here. Okay, I'm gonna do number 1 and 2, because I feel like these are really good questions to ask, where this is dealing with, there's a bypass capacitor there, so it's already going to be without degeneration. That should come into mind. And these are probably the problems you're going to see, some type, and then some partial. So here, it says, let me redraw it. So this will be handout 5. Or 1. No, that takes way too long. I can calculate worst case scenario though, like just doing calculations at the end if you want to. I can do the homework 8 one. And then let's go into this. So this is a 12-volt supply. And 300K. And then 40K. And then we have here, we got the input voltage. And then 100K. And then we have a 15K. Then this is going to be your output voltage, so out. And then this is a 2 and 3, 9, 4, 7. So find IC, VCE, and the mode of operation for this. If active mode, find R in, R out, and AB at 25 degrees Celsius per typical device. So let's find IC. So what type of design is this? Well, okay, I'm looking at it. And is this mode of operation? Find R in. Okay, so for this one, he must have used DC as the input voltage because it's not specified. And so therefore, we're going to assume just DC. And if it was an AC voltage source, then you would treat this as a common emitter with full without degeneration. And so this one, though, because there's no AC supply, we're going to just treat it as a stabilized DC model. Reason why is, if you remember from 211, X of C is equal to 1 over omega C, which is equal 1 over 2 pi F of C. And then the frequency at 0, specifically frequency, when you have 0, when it's DC, that has a frequency of 0, it'd be 1 over 0, which is equal to infinity. So this would be infinite impedance in parallel 15K, and it'd only be 15K. And so we're in a stabilized DC model. And for this, we have to determine IC. Well, IC is equal to VRC all over RC, which is going to be equal to, we said IC is approximately IE when we were going at it, which is VRE all over RE, which is going to be equal to VThev minus VBE all over, and then RE, which is equal to, then VThev is equal to VCC, and then it's R2 all over R1 plus R2 is 12 volts times 100K all over 100K plus 300K. That's equal to 1 over 4 times 12, which is 3 volts. So we have 3 minus 0.65 all over the emitter resistor, which is 15K here. Your IC is now equal to, and then 3 minus 0.65 divided by 15,000 is 156 microamps, or 157 microamps if you round it. And so what we're going to look at now is IC max. IC max is going to be equal to VCC all over RC, which is going to be equal to 12 volts. Makes sense because we're dealing with an NPN transistor. P positive, we need positive voltage at the supply. So 12 volts all over RC, which is going to be 40K equals 12 divided by 40,863, just 300 microamps. And so now that we got that, we know IC max is greater than IC, so we have active mode. Now that we got active mode, we found IC here, VCE, what is it going to be? Well, VCE is going to be equal to VCC minus IC times RC plus RE, which equals 12 minus, and then here IC is going to be 157 microamps. Okay, yes, times RC plus RE, which is going to be 40K plus 15K. 12 minus 157 e to negative 6. Times, then 40K plus 15K is 3.365 volts. And then now that we got that, 3.365 volts, we got IC, VCE. Now let's determine R in and R pi, and sorry, R in, R out, and AB at 25 degrees Celsius. So because now he said R in, R out, and AV, those are AC parameters. That should come to mind right there. So because he specified AV here, R in and R out, that's now dealing with AC. And so since he's dealing with AC, but remember, DC parameters are the same for any type of model. And so that's what's nice, is these values are still the same. But now, because I recognize in the question, he's asking for R in, R out, and AB, he's wanting AC. And so look at the AC parameters here. What I would say is, well, what is this? If this is AC. If this is AC, then this is going to be specifically for our AC parameters. What type of model is it? Well, it's going to be a common emitter without degeneration, because this is a bypass capacitor. So common emitter without degeneration. Let's see, our R input is going to be equal to little r pi in parallel with R1 in R2. And so let me see. Yeah, I got it. Okay. I know you're just gonna have to practice these formulas. And then R out will be equal to RC in parallel with little RO. And AV will be equal to, and then it's gonna be, because we don't have substantial gain, so it's gonna be equal to specifically negative VRC all over VT. This R pi is going to be equal to beta naught VT all over IC, which is going to be 1.2 times beta DC. So 1.2 times 200 for 3947 times VT, which is 0.026 all over IC, which is 157 microamps. I got 39.75 kiloohms. And now that I got that, for my R pi, let me try finding my R in total. So 39.75 kiloohms. Parallel with R1, which is going back from our model up here, it's 300K, and then in parallel with R2, which is 100K. It's equal to times got 25.9 5.978 kiloohms. R out is going to be equal to RC, which is 40K, parallel with 380 all over, because remember, RO, little RO, is equal to VA over IC. VA is usually around 380. That's what I use as my value. That's just a just remember that one for VA. There's a lot to remember. But your IC here calculated was 157 microamps, which R out is going to be 40 e to the 3 times, and then 380 divided by 157 e to negative 6 divided by 40 e to the 3 plus 380 divided by 157 e negative 6. Okay, I got 39.35 kiloohms. Where we're good. Okay, we are good there. And now that we got R out, R in, let's determine the voltage gain. AV is equal to negative VRC over VT, which is going to be equal to negative IC RC all over, and then VT, which we know is 0.026 at room temperature. IC is going to be equal to, what do we have here? It is 157 microamps. RC is 40K. 0.026. $241.5. And so now we got that. And then now that we got the gain, we got the R in and we got the R out. We found everything for it. So my R out here, I'll circle the gain here, and our R in. Okay. Now let's do number 2. Okay. Everyone doing good? Okay, we'll get to number 2. So let me just start. So we have 50K, just write that out. So 50K. We have 12K. We have output. We have okay. We have 10K here. So 2N, 2A. And so what we need to do is we need to find IC, VCE, RN, R out, and AV. And so what we're going to have here, here's 20 volts supplied. And then we're going to have IC is equal to, well, let's try determining which model this is first. Because he's asking me for RN, R out, and AV, he's referring to an AC parameter. So therefore, we know we're going to be working with a device that has AC. And this is stabilized model. And this bypass capacitor makes it a common emitter without degeneration. And this is an NPN transistor, positive voltage. Yep, that checks with the supply. And now we got IC is going to be approximately IE, which is going to be VRE all over RE, which is going to be VTheb minus VBE all over RE. Now we got that. So VTheb is equal to VCC R2 all over R1 plus R2. It's going to be equal to 20 times 10K all over 10K plus 50K. Equals 20 times 10e to the 3, 50e to the 3 plus 10e to the 3. Now we got 3.33 volts. And so now that we got that, we're going to do 3.33 minus 0.65 all over RE, which is 1K. $2.68 millivolts. IC is approximately 2.6 milliamps, sorry. And so now that we got that, we need to determine our IC max to check if it's an active or saturation mode. It's going to be VCC all over RC, which is going to be equal to 20 all over RC, which is 12K. 20 divided by 20. About 1.67 milliamps. Okay, now that we got that, this one, IC is greater than IC max. First case of that is greater than IC max. Therefore, we are in saturation mode. And so the max that you're going to get is, remember, ICEO is equal to beta DC times ICBO. And so now we know this gain is for the 2222. What is that? Because okay, what I have for mine, let me check, is I have 2 nanoamps I know for sure for this current. Because it's a 2N. From one semi, it's like the beta DC at room temperature, because we're at 25 degrees Celsius. It would be, we have 2 nanoamps for base current. It's going to follow a similar pattern, but looks like we're going to be pretty low here, like around 80 maybe. But this is with the ICBO, but it looks like our typical, I would say, because usually operate on 1 milliamp, but because this is 2 nanoamps times whatever. Let me see, do they have other curves? I want to judge it, but ICBO, it says it's about 0.01 microamp, so about 1 nanoamp. We're right with that. And then give me a beta DC or anything. ICBO, if it's like, I'm thinking the gain's going to be pretty low around here, because for the lowest one, for 1.1 milliamp, this one's a weird, so since we're in saturated mode, this is the max current that it can ever deliver. And so therefore we do VCE is equal to VCC minus IC times RC. Because remember, this is the effective combination of these two. So this capacitor should cancel out this one. And so what we're going to see is it's going to be VCC minus IC RC. And this would be 1.67 milliamps. Oh. Okay, give me a second real quick. Let me switch my computers real quick. Now that we covered that, in order to see, well, now since it's in saturation mode, basically what we can say from this is that once we got that, we can calculate R in, R out, and AB. Well, R in is going to be equal to, well, let's think about this. This capacitor bypasses this resistor here. So therefore, since it's bypassed, what's going to happen is that our R input equation is going to be different. Remember, this is the common emitter without degeneration. So AV is going to be equal to negative VRC over VT. R out is going to be equal to, and then RC in parallel with little RO. R input is going to be equal to R pi in parallel with R1 in parallel with R2. Which is going to equal, well, let's calculate R pi. R pi equals beta naught VT all over IC. And so this is going to be 1.2 times, and then what we determined here for our beta naught, since it's in saturation mode, the max current we're going to get is 1.67 milliamps. So looking specifically at the transistor curves, what I would say for 1.67 milliamps is going here, 1.67 milliamps right here, round right in this value. So I would say 150 for yours. Aren't we not supposed to? Well, that was for the first one. And so the second one said, didn't specify it. And so that's why I'm just solving for it in case. If not, then we don't have to. But in case you want to make sure that you know a way to, so that's why. So that's why I chose my 1.2, and then I looked up my beta naught of the saturated mode, which is 1.67. And when I looked on the transistor data sheet, when I looked at 1.67, I got approximately, for 25 degrees Celsius, 150 DC current rate. And then my VT is 0.026 because it's at room temp, all over IC, which is 1.67 milliamps. R pi. So your little R pi is going to be equal to, if you do that calculation on your calculator, what you're going to get is 1.2 times 150 times 0.026 divided by 1.67 e to the negative 5. And get 2,802. Now that we got that, we got 2,802 parallel with R1, which is 50K, and parallel with 10K. That's going to be times 50 e to the 3 divided by 50. Hey, we got 2097. And then here we got RC, which is 12K, parallel with 380 all over IC. Well, IC, we're using our max one, which is 1.67 milliamps because they go into saturation mode. This is what I would assume. Times 380 divided by 1.67 e to the negative 3. And then divide by 12,000 plus 380 divided by 1.67 e to negative 3. And I got about 11,398 ohms. And then here for your voltage gain is negative IC RC, and then all over VT, which is 0.026. Negative IC would be 1.67 milliamps times RC, which is going to be 12K, all over, and then your 0.026. 12 e to 3 times negative 1.67 e to negative 3, and then divide by 0.026. Negative 770 is your gain. Okay, then we got our out, and then we got our input. So I did this just in case you might have to do a calculation where it's in saturated mode and you're like, what do I do now to get my R in, my R out? And so now that we went over that example, which is like that extraneous case, let's do number 6, and let's look at what this one has. So let's do, I think what we focused on was the first few. So let me do 1C and 1A maybe. Those look like different ones that might pop up. So trying to identify what type of models. So 1A from this is handout 6. 6, and let me flip over here. So for 1A, you have 4 mega ohms. And then you have negative 10 volts. 10K. Then, oh, sorry, opposite way, this transistor, so let me draw it just this way. And then ground. And so here, what you have to do is to get your IC, what type of design this? Well, this is unstabilized because there's no emitter transistor, there's no actual resistor there. And then we have to determine IC is going to be equal to, and then this would be V RC over RC, or you can remember the equation IC is going to be equal beta DC times IB. And IB is specifically given as IB equals BRB all over RB. And knowing that, we can determine the emitter of the base, the emitter resistance is 4 mega ohms. And then here for VRB, it's VCC minus, and then voltage between the base and emitter, which is going to be negative 10 plus 0.65 all over 4 mega ohms, which is negative 10 plus 0.65 divided by 4 e to the 6. And then what I got from my IB is it's equal to negative 2.3375 microamps. And so my beta DC here is 200 times negative 2.3375 microamps. What I would get as a result times 200. Negative 467.5 microamps. 67.5 microamps. Okay, what we got here is now we got IC, we got IB, VCE. It's equal to VCC minus IC, or and then C, which is going to be equal to negative 10 minus, and then here is negative 467 microamps times RC, which is 10K. And then here we get VCE, which is negative 10 minus this value times 10K, negative 5.325 volts. Okay, we got this value, and now we know IC and we know VCE. And so that's good. Let's just make sure IC though with IC max, that's always a good thing. Just try and get in the habit of doing that. Is VCC over RC. which is equal to negative 10 volts all over, and then RC is 10K, is negative 10 divided by 10K, which is negative 1 milliamp. Negative 1 milliamp IC max compared to IC max is greater than IC. So therefore, what we're going to see here is negative 467, negative 1 milliamp is greater than negative 467 microamps. So therefore, IC max is greater than IC. So then we can say this is active mode. And so now that we have this, we got the operating point, we got IC right here, got VCE, and we determined the operating point. Let's now do 1C. That one looks interesting. So this configuration, he gave it to us sideways. So let me just try drawing it the other way. Still the same thing. 2K here. And then here we have 15. Okay. And then here we have ground. Then we have 50K. And then here we have 5K. And then we have 12 volts. Okay, now what we need to do here is we got to do division. So real quick, let's just convert this over to the other way. And so what we're used to seeing it. So like in this configuration, let's do that here too. And so if I'm gonna just flip flop everything here, 50K at the top, then we're gonna get 50K here, 5K here, 12 volts, and then we have here, this one, and this is leads to 2K. And then we have 15K. Oh, and so we're used to seeing the 15K. We can draw it actually like this, so it actually makes more sense. I would just redraw it so you actually understand the circuit. And then what we notice, oh, wait, let me see. This 12 volts is in between the 50K and the 5K. Oh, okay. So this is where this 12 volts should be. And now we can draw it finally so we actually understand the common design, what it looks like, what we're used to seeing it like. Here we go. 12 volts, 5K, 50K, 15K, and then 2K. Okay, now we finally got it. Now looking at this, this is a stabilized design, right? Got all the points, and so we can say this is stabilized. It doesn't have an input, so I'm guessing we don't calculate AC parameters here. It doesn't specify RN, ROut, or AB. And so it just wants the IC and VCE, and those are the same for all models, like I told you. And so let's do IC, that's equal to, and then V, it's approximately IE, which is equal to V Thev minus VE all over I RE, which is equal to, well, V Thevenin is VCC times R2 all over R1 plus R2, which is equal to voltage supply is 12. Remember, this is an NPN transistor, so it makes sense we have a positive voltage supply, times R2, which is 15K, all over 15K plus 50K. Then we have here is 12 times 15e to the 3 divided by 15e to the 3 plus 50e to the 3. Then we got 2.76. 77. Got 2.77 minus 0.65 all over the emitter resistor, which is 2K. And so now we got this, we can solve it and do 2.77 minus 0.65 divided by 2000. So when I do this on my calculator, oh, sorry, I keep doing divide by 200 for some random reason. I get 1.06 milliamps. Now I got IC, my VCE is going to be equal to VCC minus ICR, and then this would be RC plus RE, just going to be 12 minus, and then this would be 1.06 milliamps times RC, which is 5K plus 2K, which is going to be equal to, and then this would be 12 minus 1.06. So 12 minus, and then this value times 7K. I got 4.58. And then just make sure IC max along with this. Just keep repeating those. Like I tell you, just check everything. Make sure you're within those bounds. That's equal to 12 all over RC, which is 5K. Which 12 divided by 5K is 2.4 milliamps. And so here we just got IC max is greater than IC. So therefore we're in active mode. Since we're in active mode, we can use the value we got here. We can use the value we got here. There we go. That's what we got for IC and VCE. Okay, we're good there. Now let's get to the next ones, which are on handout 7. Let's do some partially degenerated because we haven't done that yet. So let's do C. And let's do part E, which it wants to find a capacitor value. So let's just try finding one of those because we haven't done that yet either. So let's start, let me switch over here. So let me copy this real quick. So we're gonna do handout number 7, which is actually funny how many of these were stabilized designs. And we were just looking at them in a different manner because we didn't know how to split it up into, what was it called? Common emitter with full degeneration, partial, no degeneration, common base, common collector. We didn't know till just a few lectures ago. So all this time we were just dealing with these stabilized configurations or common emitter just with partial degeneration. We didn't know these other types existed. So that's cool. Okay, so for 1C, I have 180K. And then we have 60K. And now we have 2 and 5, 0, 8, 9. Then we have 7K. 12 volts, and then this is 350 ohms. And then this is 2K. Then we have here, what are we gonna do? Well, let's see. What we have is, let's see. We need to determine IC, VCE, AV, RN, and RL. So let's look at this. So this design, it's a common emitter with partial degeneration. So how do you go about solving one of these? It's going to be, when I see this, I'm going to say that IC, remember we and say IC is approximately IE, because that's the DC model. You can apply these equations anywhere, which is equal to VRE all over RE, which is V sub minus VBE all over RE. V sub is equal to VCC all over R2 all over R1 plus R2. And then VCC is 12 times R2, which is 180K all over 60K plus 180K, which equals 12 times 180 divided by, and then 240, 9 volts. So we got 9 volts here minus 0.65 all over the emitter resistor, which is, in this case, the emitter resistor is going to be RE1. If you think about it, because the impedance of this is going to cancel to 0, right? So the majority of the resistance that is going to be seen is just 350, because this is the effective impedance of this will cancel out to 0. And I think I mentioned that.
I didn't realize that I would fucking die from falling. I thought there was no fall damage.
What?
Yeah, definitely is.
Ryan, shouldn't this be 60K over that value? This should be around 3 volts.
Yeah, you're right. Yeah. Thanks for the catch. Sorry, it's being late. Okay, so this would be 60K over 60K plus, so when I do 12 times 60 divided by 60 plus 180. 3, thanks.
Yeah.
And then 3 volts, 3 minus 0.65 all over. And then RE1. Does that make sense to you guys? Because the effective impedance, majority of it will go through here, and then there's going to be about 0 volt drop due to this capacitor here. And so it's going to be pretty small there. It's not going to be large. Wait, let's see. Did we take it into account though? Okay. Okay, sorry, never mind. What we need to do here is RE. And so this would be IE is equal to V7 in here. We determined was specifically 3 volts. And so 3 volts minus 0.65 and all over the emitter resistance. This is correct now. Why I'm thinking about it is because it's not just RE1. Because if you're thinking about this in DC, because IC corresponds with the DC operating point, right? So this would have 0 frequency. So therefore, the effective resistance would just be the 2K. So that's why RE includes both the 2K and the 350. That's why we get 2.35K all over 3 minus 0.65. 2.35 volts. 2.35 divided by 2.35 e to the 3. I get 1 milliamp. Okay. Now that we got IC, let's check IC max versus it. IC max is going to be equal to VCC all over RC, which is going to be equal to 12 volts all over, and then RC is 7K, which 12 divided by 7K, about 1.714 milliamps. Now that we got IC max, we can determine that IC max is greater than IC, so it's in active mode. And what you guys need to do now is you need to determine the value for AV, R in, and R out. So remember, keep your formula straight here, because we can confuse them very easily. And so that's the one issue. And I know it's hard to keep all these in mind. So at the start of the exam, I just suggest you write out all the formulas so you don't mess them up when you get nervous and you're solving the problem. So it's negative RC all over 1 over GM and then plus RE1. This is the factor where we have just RE1, because if you think about it, the gain RE1 here, this one's going to be effectively 0 due to the impedance, and this is where the 350 is only consistent. That's where I was messing it up, over negative RC. So RC in this instance is 7K. GM, now we have to find out what GM is. It's IC over VT, which is going to be equal to, and then here we determine IC was 1 milliamp all over 0.026 which is 1e to the 3 divided by 0.026. 38.46 milli. And then if you do the 1 over that, you're going to get 26 ohms. You get negative 7,000 divided by 26 plus 350. You get negative 18.6. R in here. R in is going to be equal to, well, this is partial degeneration, so we're actually going to have an emitter resistance, some voltage drop across that, so we actually do include it in the equation. So it's going to be R pi plus 1 plus beta naught RE in parallel of R1 in parallel of R2, which is equal to, well, our R pi here is equal to beta naught VT all over IC equals 1.2, and then our gain. What is the gain for the circuit? Well, we're using a 2N5089. So let's look at the data sheet. 2N5089 data sheet. Here we go. And if we're looking at the characteristic curves here, DC current gain for about 1 milliamp. Here we go. Here's 1 milliamp. Room temperature, it looks, oh man, this is not the best. It's right about here. So wherever this curve is right here. So this would be 200, 300, 400, 500, 600. I'm going to say 600 times 0.026 all over IC, which we determined up here was 1 milliamp equals, and then here we get 1.2 times 600 times 0.026 divided by, then 1 e to the 3. I got 18.72 kiloohms. So I got 18.72, and then do plus 1 plus beta naught. Beta naught is going to be, well, we just termed it here, 1.2 times 600. And then with that value, multiply it by, so I got 20.04 when I plug that in, okay? In parallel with R1, which is 180K, in parallel with R2, which is 60K. Okay. So times 180K.
Yo, for R in, shouldn't it be R pi plus 1 plus beta naught times RE1?
Or E1.
Yeah, I think you forgot the RE1 for the R in.
Yeah, you're right. That's the only one I consider. Thank you. Sorry. 2 review
Dude.
sessions in one day is just killing me.
No,
Okay.
no, you're chilling, bro.
1 plus, hopefully this is helping. I'm not giving you guys like wrong answers and like, sorry. No. Okay, sorry. 1 plus beta naught, which is, we determine beta naught here is 1.2 times 600, and then times RE1, which is given by 350. Well, at least you guys won't make the mistakes during the exam since you know it now. Plus 18.72 e to the 3. Okay, I got 270.72 kiloohms. Did you guys get that? I don't know how I'm getting that though. So I'm getting 350 multiplied by 1.2 times 600, and then plus 1, and then plus, and then 18.72 kiloohms. Okay, I'm getting 271 kiloohms. Anyone tell me if you're different? That's what I got here, 271 kiloohms when I did that recalculation. Times 180 e to the 3 divided by answer plus 180 e to the 3 times 60 kiloohms divided by answer plus 60 kiloohms, 38.5 kiloohms, or 6 kiloohms here. Okay, and then now that we got R in, our output is going to be RC in parallel with little RO. And so here we're going to have little RO, well, our RC here is 7K in parallel with 380 all over IC, which is going to be 1 milliamp, which is going to be 380 divided by 1e⁻3. And then that's going to be times 7,000 divided by answer plus 7,000. Okay, that's 6.87 kiloohms. Okay, there we go. That's our AV, our RN, our R out. And then we got all the rest. We got our IC, we got our VCE, we're good to go. And so now that we solved that one, how will you determine CE if the lowest frequency is 30 hertz? And so, oh, someone has something to say?
Dude over there.
I think you have for GM, isn't it the other way around? VT over IC?
No, that
That's
one.
1 over GM.
Oh, I
Yeah,
see what you're saying. You accounted for that inversion.
Yeah,
already.
yeah, I
Never mind.
did 1 over 38.46 milli.
Yeah,
I got,
now I got it. Sorry.
okay, good. Yeah, double check me. And so find an appropriate value for CE in part C and D if the lowest frequency is 30 hertz. And so CE, that's up here. So it's saying that our frequency is equal to 30 hertz at the lowest. And so we want an appropriate value for CE. Now remember, x of C is equal to 1 over, and then you want this to be omega C. And then we have, if we write this as 1 over 2 pi f times C. And what value do we want for C? Well, we can see that if you do C equals 1 over 2 pi f times x to C, what's the effective, what do you want for this? It's 1 over 2 pi times 30 hertz, and then times, and then your value, what type of impedance do you want here? That's the true question that it comes down to be, because you get to choose which impedance you want here. And if it specifies, I know it's sometimes pretty low because it's a bypass. This should be almost like no voltage drop it's going to have on it because it's a bypass capacitor. So therefore, it's going to be pretty low. It's going to be only like 25 ohms or something. Like it's in a pretty low range, I believe. And so anything that's just low in its value. So if you did 1 divided by 2 pi times 30 times 25, I got 212 micro farads, and that's what I got. In capacitors, you should be in the microfarad range, but I just chose an arbitrary value because I knew the effective impedance is going to be pretty low. This is a bypass capacitor, and so therefore it's pretty negligible at 25 ohms. That's the only resistance here in comparison to 350, which is about 10 times it. So that's just the value I chose for CE. And so now that we talked about that, let's get into, let's see, was there a design problem that we need to do? Design pressure degenerating. Okay, let's get into handout 8 because I know we're running over time, but I know you guys wanted to know how to do minimum and maximums. Okay, it loads.
What are you doing?
Minimum and maximum problem for number 8. Okay, find the minimum in this one, John, right? You wanted to do number 3. Does that sound good?
Oh no, I was mainly questioning number, it was homework 4.
Oh yeah, no, you won't see those, I believe. This is the one I could see on there, but that's all I can get.
Okay, yeah, then anyways, yeah, if you could still do it, that'd be cool.
Okay, so handout 8, number 3. Find the minimum maximum voltage of the load, 5K. In the circuit below, assuming beta DC varies from 30 to 300 over a temperature range of -55 degrees to 125 degrees. And so what we're going to see here is beta naught is equal 1.2 beta DC, and lowest frequency is 100 hertz. So we have here our voltage source, 5K, then 15 millivolts peak to peak. And then we have 2 microfarads. And then we have 63K. Then we have 4K. Then we have 400. Then we have this one down here. And then we have this capacitor. So 40 microfarads. And then he gave us the value for this capacitor. He emailed it to us. Let me check. If anyone has a top head, drop in their chat, but I will go back and find it.
Like 2.6.
6K. Yeah, thank you. 2.6K. Got it. 37K. And then we have 3.3 microfarads. And then we have 5K. Okay.
Gosh.
Okay. Now that we got that, says beta DC varies from 30 to 300, and the temp is from -55 degrees Celsius all the way to 125 degrees Celsius. And then lowest frequency, so F low is equal to 100 hertz. Okay. Now let's start. So first thing I would say, look at this in general and determine what type of configuration it is. When looking at this in general, just ignoring the input and the output, just look at this part here. That's a common emitter configuration. And it has partial degeneration. So now that we know that, let's look at how do we solve this. And so my biggest thing I feel like to start out is, oh, this is actually a good one because it forces you to understand how it gets the voltage to the load. So let's look at the minimum values first, okay? Let's just look at the worst case scenario for the minimum. And so if we're looking at the minimum here, what we're gonna get is IC is approximately IE, right? Which is V fab minus EVE all over RE. V fab equals VCC R2 all over R1 plus R2 equals 10 times R2, which is going to be 37K. Did it right this time. All over, then 37K plus 63K, which equals, and then calculate it, 10. Got 3.7. Plus 3.7 minus 0.65 all over RE, which the emitter resistor here, 400 plus 2.6K. Reason we count both of them is because we're in DC mode, and in DC mode, remember, what is happening is this capacitor is going to be infinite impedance. So therefore, it's going to take this route. So therefore, you add both of them. So this one is a 2.6K plus a 400. So that gives me 3K. 3.7 minus 0.65 divided by 3,000. 1.017 milliamps. And then here we go. With the minimum, we got IC, we got VFEB, we got VCE, which is equal to VCC minus IC, and then RC, and then this would be plus RE, And what we're going to get here is it's going to be equal to 10 minus, and then we just solve for this 1.017 milliamps times RC, which is 4K plus, and then 3K, right? Is 400 plus 2.6. This is a DC operating point, VCE. So that's why we add both of them. So 10 minus this value times 4,000 plus 3,000, 2.88. VCE is equal to 2.88 volts. Now that we got that, we can determine specifically, got IC, we got VCE, and now we can do our amplifier. AV. There we go. Okay. Now that we got this, okay, and what's going to happen here? Well, we're going to see that we need to calculate how much voltage actually gets to the amplifier itself. The reason I drew this diagram is because it shows you how much voltage from this input is actually going to get to the base. And that's determined by these two resistors. How much is your RG? How much is your RN? And so what we need to determine is now our AC parameters. AV is equal to, and this is partially degenerated. And so we know AV is equal to negative RC 1 over GM plus RE1, which is equal to, my RC is 4K. And then I haven't determined my G of M. Let me calculate that right here, IC over VT, which equals, and then right now we're at worst case scenario, right? So this needs to be 0.019 coldest temperature. My IC is going to be 1.017 milliamps. That gives me 53.52 million. 1 divided by that gives me 18.6. Plus RE1, which is 400. Negative 4,000 divided by 18.6 plus 400. Negative 9.56. Now that we got that, Rn equal to R pi plus RE1, 1 plus beta naught R1, R2. And then R pi is equal to beta naught VT all over IC. 1.2 times 30 times 0.019. We're working with worst case scenario right now. That's the lowest gain, lowest temperature. And then IC is 1.017 milliamps. R pi is equal to 1.2 times 30 times 0.019. 672.56. So I'm just going to say 672, close enough. So we have 672 plus RE1, which is going to be 400, times 1 plus 1.2 times 30, worst case scenario, parallel with R1, which is 63K, and parallel with 37K. There we go. So if we do this addition, it's 400, and then 1 plus 1.2 times 300, or 30, sorry. I got 15K about in parallel with 63K. And then in parallel 37K. I got 9.30 kiloohms. There we go. Now that we got that, we have our input, we have our, now let's see how much voltage is actually given there. So voltage input is going to be voltage base times by Rn all over Rn plus Rg. And then we're going to have voltage at the base, which is going to equal, this is going to be specifically, well, how much voltage is actually coming in? 50 millivolts peak to peak. 50 millivolts peak to peak times Rn, which is 9.30K, all over 9.30K plus Rg, which is 5K. That's the source resistance, which was given up here for the 5K ohm. Now that we got that, that gives us our voltage input. Times EE330. I got voltage in is going to be equal 32.52 millivolts peak to peak. Now that we got the voltage input, we got to get how much actually gets to the load resistor. So first we have to calculate from here. It's R out. We have to calculate that, find out how much of that voltage is on the load resistor, just 5K. So R out is going to equal RC in parallel to little RO. Little RO is equal VA over IC, which is 380 all over IC, which is 1.017 milliamps. That equals 380 divided by that. 373 kiloohms. So we got 4K parallel with 373, sorry, kiloohms. And so if I do the parallel combination of those two, what I'm going to get is times 4K divided by answer plus 4K. 3.96. Okay. Okay, now that I got R out, now we need to determine the voltage on the load resistor is going to be equal voltage out times load resistance all over load resistance plus R out. So this is now going to determine our output voltage is going to be, we determine, how do we find the output voltage? It's going to be the gain multiplied by the input voltage, right? So the gain we found was negative 9.56. The input voltage we found was 32.52 millivolts. That makes sense because the output would be equal to the input times the gain. And that goes back to sort of like your operational amplifier a little bit. So V out would equal, this would be negative 9.56 times 35.52 to negative 35.52 even negative 339.57 millivolts peak to peak. Negative 339.57 millivolts peak to peak times the load resistor, which is 5K all over 5K plus R out, which we determined was 3.96K. And so now that we got that, voltage at load resistor equals, and then here would be 5,000 divided by 5,000 plus 3.96 e to 3. Negative 189.49 millivolts peak to peak. Now that we got that, we can determine our next set, which we got the load resistor voltage here. Let's now determine how much, because this is our minimal. When we did like the temperature, -55, we did VT equals 0.019. Now let's find the maximum. So we just got to repeat that whole process. Everyone's probably like, gotta do it. Maximum. So the maximum is going to be I of C, which is going to equal I of E, which is approximately IV, which is V dev minus VBE all over RE. RE in this case is 3K, that seems the same. Now we need to make sure VThev will stay the same, so it's still 3.7 volts as we calculated above. VBE is still 0.65, so that's 1.0, and then 17 milliamps. VCE is going to remain the same. Nothing's dependent upon temperature there, so that would still be 2.88 volts. What's going to change is your AC parameters, and that makes sense. Your DC should stay the same. They're not dependent upon having all those values for this specific configuration, but we're going to see that our AC parameters, that's where it's going to start varying. So what we're going to see for the AC is it's going to be AV is equal to negative RC all over 1 over GM plus RE1, which is going to be negative, and then our RC collective resistor is 4K. And then remember, GM, this is where it's going to change. IC all over VT, which equals 0.035 worst case all over IC, which we had was 1.017 milliamps. Divided by that, let me redo. About 29.057 milli. And divided by that number is 34. Plus RE1, which is 400. Negative 9.2. Negative 9.22. Now that we got AV, we need to get GM. No, sorry. Now we got AV, we need to determine our other parameters, which is Rn, which equals R pi plus RE1, 1 plus beta naught, R1, R2. And R1 in parallel of R2 is given by 63K in parallel with 37K. 1 plus 1.2 times. And then here the max gain is 300, they told us. RE1 still stays the same. Plus R pi is equal to beta naught VT all over IC. Just 1.2 times 300 times 0.035 all over IC, which is 1.017 milliamps, equal to 1.2 times 300 times 0.035 divided by 1.017 e to the negative 3. Oops. 1.2 times 300 like 1.017. Okay, 12.39 kiloohms. 12.39 kiloohms plus 400 times 1 plus 1.2 times 300 times 63 e to the 3 divided by answer plus 63 e to the 3 times 37 e to the 3 divided by answer plus 37 e to the 3. Okay, I got 20.29 kilo ohms. Got R in. Now we need to determine R out. RC in parallel with little RO, which we know, oh, that stays the exact same as the, wait, yes, it does stay the same. So I'm just gonna use that value. And so now we got that. So now if we draw our amplifier, within an amplifier, we got AV, we got R in, RG, and then we got R out, and we got R load. Now what we need to do is we need to determine how much of that voltage from the input actually gets to from the base. And so that's going to be our R in, all of R in plus R load. It's going to be voltage on the base, which is in this diagram, it was given as 50 millivolts times R in, which R in is going to be, our load is what we want, just 5K. Our input is going to equal 9.30K, or sorry, I'm using that one, R1. Our in is 20.29K. 20.29K all over 20.29K equals, and then so what we're going to see here is 20.29 divided by 20.29K is 5,000 times 50 e to the negative 3. 40.12 millivolts peak to peak. Now that we got that, we got voltage input. Voltage output is going to equal the gain times the voltage input. It's going to be equal to negative 9.56 times 40.12 millivolts peak to peak. So this would be negative 383.51 millivolts peak to peak. There we go. Got voltage output. And now we can determine how much voltage is on that load resistor. That's going to be equal voltage output times R load all over RO plus R load. Because it's a voltage division problem here. The out is negative 383.51 millivolts peak to peak. Our load is going to be given by a 5K over this plus 5K. It's R out. We determined from the previous page that was 373 kilo ohms. Makes sense because our we usually use common, what is it? Base or no, it's a common, yeah, common, it's a common collector real quick. Sorry. We usually use load, so we usually use common collectors in order to drive to load because common emitters have high output impedance, so that's why we don't use them much. And so here we have this times 5K divided by 373K plus 5K. And then that's equal to negative 5.07 millivolts. And so that's the maximum value I got. And so this is my max. And here, let me find the other one. Add the load resistor there. This was assuming worst case scenario is going to make yeah, everything checks up in here. I use all the correct values. So that's what I would assume. But it does show a pretty vast difference between the two. But that would be my best guess in order to approach that problem in case he doesn't share it. And then I will pause the recording.